die, I'm just going over this problem again one more time for you. So we're saying that the steady state concentration is equal to 0.002 microgram per mil, right? And we know that two processes are taking place. Two processes. We have a loading dose, and from the question you could see it's 3.14 mcg. We gave a loading dose, we worked it out. Remember the process for working it out: concentration is equal to dose over volume. So dose is equal to concentration by volume, and that's how we ended up with the 3.14. Concentration was 0.002 and the volume was 15.700. We'll convert everything to liters, to milliliters, right? So when you have a loading dose, you give a dose, over time it decays like this. Any dose that you give with time, one dose, it decays like this. If you're given multiple doses, you give a dose and it starts to decay, but then you give another dose, and you get a rise, and then it starts to decay, and you give another dose and it starts to decay. That's a multiple dose situation. That's not what we're dealing with here in this situation. What we're dealing with here in this situation is just one straight dose, and that straight dose disappears with time. So the equation we need to use, which describes a decay in concentration with time, is the same basic equation from the very beginning. We're talking about C is equal to C0 e to the minus kt. Right? We know that this C here is concentration at some time. This C is the initial concentration, and this is the reducing factor. So concentration at 48 hours is equal to the initial concentration. Now what's the initial concentration? The initial concentration in this situation, when you give the injection, one shot, bam, give the injection, it attains a steady state concentration, they told you, of 0.002. So the steady state concentration is 0.0002 multiplied by e to the minus k. What was k? We worked out k, infusion rate. What was k? Hang sec. K turned out to 0.0315 by 48. When you work out all this drama, the answer you get here would be 0.0000, I think it's 4 zeros, 1, 2, 3, 4 zeros, 4 milligrams. Alright, so this is the loading dose part of the problem. The loading dose part of the process is we get 0.0004. So now I'm going to start erasing everything. Let's go back now. So when you work this out, you will say to yourself, right, hang on. So continuing from the loading dose, right, the concentration after 48 hours was 0.000044, and we already worked out the first part of the question. What happens in 48 hours after the infusion? After the infusion of 48 hours, we use concentration of 48 hours after the infusion is equal to KO over VK into 1 minus e to the minus kt. Right, when we work that out, KO over VK into 1 minus e to the minus kt, all those questions, the figures were 0.1, we worked that out earlier on, all over 15,700, right, because we're talking about milliliters, yeah, right, into 1 minus e to the minus, k was 0.0315, 0.0315, sorry, the point is over there, right, 0.315 multiplied by 48. When you work out the maths for that, you would have gotten 0.000156. So the infusion process after 48 hours left us with a concentration of this. So the total concentration in plasma will be the sum of this and the sum of that, which is equal to, alright, when you add it up, you get 0.0002. The book has 0.00018, but 0.000, whatever, same thing.